So this lesson's on the double integral and surface area. So how can we find that? I have this region omega that's in the plane, and I have a point x naught, y naught. And I want to identify where f of x naught, y naught is. So it's in some surface that is above that plane. So let's go ahead and construct some kind of a surface. So this blue surface is z equals f of x, y. We're going to go ahead and we're going to find the point where f of x naught, y naught is, which may be right here. So that's the point f of x naught, y naught. So if we're going to go ahead and identify that point, the x value is x naught, the y value is y naught, the z value is f of x naught, y naught. Now, what do I want to do? I want to find the tangent plane to that surface at that point x naught, y naught. And I want to draw a little tangent plane there. So let's look at a similar picture to help us visualize that. So you'll notice I have, it looks like 4 points here on this surface, and then a small portion of the tangent plane was constructed at each of those 4 points. That's what I believe is happening here. So I want to construct a tangent plane at the point that I have, a relatively small one. So let's go ahead and do that. At this point, we're going to construct a tangent plane. And I would like to find eventually the area of that tangent plane. So what's my analysis here? Well, let's talk about the partial derivative of f with respect to x. The partial derivative of f with respect to x is approximately the change in z over the change in x. For small changes in x. Therefore, f sub x times the change in x is going to equal the change in z. But if we're looking this direction, there is no change in y. So if I call this vector u here, so that's typically in the x direction, right? X comes out at us, y goes this way, z comes up that way, right? X, y, z. If I'm looking at u, there is no change in y. So what is that vector u? Well, the change in x is the change in x. There is no change in y. And what did we say the change in z was? We said it was f sub x times the change in x. So that's that vector u that is going to help define our little itty bitty tangent plane. So that was with a discussion of f sub x. How about f sub y? What do we say about f sub y? F sub y is approximately equal to the change in z over the change in y for small change in y. So again, f sub y times change in y should be basically equal to change in z. Let's call this vector v. But on that vector v, there is no change in x. So the vector v I'm going to have here has no change in x. The change in y is the change in y, and then the change in z is f sub y times the change in y. So do we see how these two vectors, u and v, define that element of the tangent plane? And then we can ask ourselves the following question. Our goal is to get the magnitude of that little itty bitty tangent plane. And the magnitude of that parallelogram, right, with those two vectors is simply going to be the magnitude of u cross v. So the area of that little parallelogram is simply going to be the magnitude of u cross v. And then what we're going to imagine is we're going to imagine we have little parallelograms all over that in the region that we have that corresponds to omega. We're going to add those together to get our answers. But let's go ahead and take a look at what u cross v is before we do a whole lot more with the geometry. So there's u and v, and there's u cross v. Remember, it goes plus, minus, plus across the top. So let's go ahead and do that cross product. In the I direction, what do we get? We get 0 minus f sub x, change in x, change in y. In the j direction, we get f sub y, change in x, change in y, minus 0. So it'll be negative f sub y, change in x, change in y. And then in the k direction, what do we get? We get change in x, change in y. So simplifying that just a little bit, u cross v is negative f sub x, change in x, change in y. Negative f sub y, change in x, change in y. Change in x, change in y. Notice something about this, that there is a change in x, change in y in each slot so that I can pull that out. So what I get is I get u cross v is change in x times change in y. What's left? Negative f sub x, negative f sub y, 1. This is my u cross v. So then what is my magnitude of u cross v? Well, it's actually absolute value of change in x, change in y, which I'm going to choose to ignore here shortly, times the magnitude of that vector, which is what? Which is the square root of negative f sub x squared, which is the same as f sub x squared, plus negative f sub y squared, which is f sub y squared, plus 1. So assuming the change in x and change in y are positive, I'm going to relax that a little bit. So the magnitude of u cross v will be the square root of f sub x squared plus f sub y squared plus 1, change in x, change in y. Now that was just for one single point, right? That was for one single parallelogram. But if I come back here, if I take all of these points, they will live somewhere up in this surface. So these points get set up here. So there's a point that goes here. There's a point that goes here. There's a point that goes there. Each one of those will also have a parallelogram. And if we add up the areas of all those parallelograms, that will give me the surface area above this region, omega, within that surface, z equals f of x, y. So the total surface area will be the sum of all of these things. Now we have a sum, we would rather use an integral, so this is essentially a Riemann sum. So we shrink delta x and delta y to 0, and that will go ahead and give me an integral. And what will that integral be? Surface area will equal the double integral over our region omega times the square root of f sub x squared plus of f sub y squared plus 1 delta x delta y becomes dx dy. So that's our formula. And let's use it to solve the following problem. So our question is to find the surface area of the plane z equals 8 minus 4x minus 2y above the first quadrant. But let's try to visualize that. So here is that portion of the plane in that first octant. So I need to determine what is my region of integration. We're going to have to determine what that omega is going to be. Now it might help to take a look at it here, from above. Not always perfect here on this app, but we can go ahead and do the analysis to find out what that is. If it sits in the xy plane, what do we know? We know that z has to be 0. So if we're looking for the shadow of this in the xy plane, set z equal to 0. So z equals 8 minus 4x minus 2y. 4x plus 2y equals 8 is what I'm looking for. And then I think it's actually nice if we divide everything by 2. So that gives me 2x plus y equals 4. And if we're looking at this, then what do we have? X would go out to 2, and y would go up to 4. And this would be our shadow in the xy plane. So here's 2, 0. Here's 0, 4. If I project this down into the xy plane, this is what I'm getting. And I hope that is in essence what it looks like when we look at the graph. And sure enough, x basically out to 2, y basically up to 4 for that projection onto the xy plane. And then there's our three-dimensional version of this. And we want to go ahead and get the surface area of that portion of the plane. So let's work on that. So we know what our formula is. We know what our z is. So let's do our analysis. My function f of xy is 8 minus 4x minus 2y. So f sub x is minus 4 and f sub y is minus 2. Okay, well, that's nice. I have that. Now, there's the formula I'm working off of. So I need to determine my region omega here. So we've got to look at the fences. The southern boundary of this is the x-axis, is y equals 0. The northern boundary is 2x plus y equals 4. Solving for y equals 4 minus 2x. So this is y equals 4 minus 2x. So in terms of setting up our region, we are going to get what? Y ranges from 0 to 4 minus 2x. X, what is the smallest x I see? What is the largest x I see? Smallest x I see is 0. Largest x I see is 2. Then I have square root of f sub x squared plus f sub y squared plus 1, and I'm going to go dy dx based on this order. So let's go ahead and do that integral and see what we get. So here's the information we have. I need the square root of f sub x squared. Well, f sub x is negative 4. If I square that, I get 16. F sub y squared, f sub y is negative 2, squared is 4, plus 1 dy dx. So now my problem becomes SA, surface area, is x goes from 0 to 2, y goes from 0 to 4 minus 2x of the square root of 21 dy dx. So let's do the inner integral over here. The inner integral is the integral as y goes from 0 to 4 minus 2x of root 21 dy, which of course is root 21y as y goes from 0 to 4 minus 2x, which is root 21 times 4 minus 2x. So that's my inner integral, so I'll replace that here. So now I have SA, surface area, equals integral as x goes from 0 to 2 of root 21, 4 minus 2x. Pull the root 21 out in front. My antiderivative of 4 is 4x minus my antiderivative of 2x is x squared. Evaluated as x goes from 0 to 2. So surface area is root 21. 4 times 2 is 8. Minus 2 squared is 4. Minus 0 minus 0, which equals 4 times the square root of 21. And that is my surface area of that portion of the plane in the first octant. Or if you like, we can consider that the area of that triangle.